Okay, so let's do the actual derivation for these equations. Okay, so we're going to do the charging situation. So we start with initially, so the Q on the capacitor at t equals 0 is 0. And our goal is that we want to get a function for the charge on the capacitor as a function of time. Okay, so let's just start by recognizing that the loop rule is, at t equals 0, the switch is closed. So then the capacitor will start charging. So when you look at the loop rule, you can see that the EMF of the battery has to equal the voltage across the resistor plus the charge on the capacitor divided by the capacitance, because that's the voltage across the capacitor, right? So at every instant, this is true. So we can recognize that current is really dq dt, and here we are. And so now this is calling for separation of variables and eventually u sub. So let's get dq dt by itself. So our dq dt is the EMF minus q over c. And then let's get all the q's on one side and all the dt's, and we'll throw the 1 over r over there as well. Okay, so that is how we separate our variables. And now I look and I say, ooh, I need u sub. So let u be the EMF minus q over c. So du is negative 1 over c dq. So that means I can figure out that dq is negative c du. Sweet. So I'm going to write that in here. Instead of dq, I'm going to say negative c du, and then that's u on the bottom. That's 1 over r dt. If it's okay with you, I'm just going to throw that constant over there. So negative 1 over rc, and that probably is looking pretty familiar at this point. Let me move this up. So let's integrate these, okay? So that's going to be log of u, right? But because I want to get my limits in there, I'm actually just going to throw my value of u back in there. So what was that? Oh, it's over here. So log of the EMF minus q over c. And where are we going? We're going from that initial situation. Sorry, I'm going to, my integral of dt is from 0 to time t, right? And here my initial q was 0, and then we're going to go to, right, that q of t, which is what we're looking for. Okay, groovy. So I have log of the EMF minus q over c minus log of just the EMF, right? Because the q is 0 for my bottom limit. And then this is just going to be negative t over rc. All right, then we use our nice thing about subtracting logs. We go e minus q over c for e, and we get negative t over rc. So we get log of 1 minus q over ce. We get negative t over rc. Now we're going to raise both sides. Or sorry, we're going to say e to the both sides. You know what I mean, jelly beans. So we just get 1 minus q over ce and e to the negative t over rc. My gosh, this is getting messy. Sorry about that. Okay, so we got to switch some stuff around. So q over ce. So if I pull that to the right, get rid of that negative, and then I pull the exponential to the left, even though I just wrote these on the left and right sides, opposite of what I just said, I believe you know what I'm doing. And then yay. And remember, this Q is Q of t, and I just haven't been writing the of t because it's messy. And here we are, 1 minus e to the negative t over rc, which is the thing that I basically asserted. So Q versus T, it starts at 0, looks like that, and the asymptote is the capacitance times the voltage of the battery, which is the maximal value of Q.